All right, so I guess we'll get started.
All right, fantastic. Well, so welcome everyone. It's my great pleasure to introduce James for his PhD defense. James comes to us from doing his earlier research on thermoelectric materials for a startup company in upstate New York. And I remember him coming to visit and everybody's like, man, this guy is like perfect for our group. And he was like, yeah, I've been working on this for a while and I'm not really sure I want to do this for a PhD. And normally I don't suggest anybody, really continue, it's a good chance to change to a different topic for a PhD, right? But then, after looking around, we both concluded that, well, this is totally going to work as a great PhD anyway, so let's do it. And I think what happened is, James really fit in really quickly with the group. He could make his own samples, start doing some fine tuning of materials, which we'll hear about, and also then move into new areas that were, his own design. And so you'll hear also about some of the mechanical properties. So in the end, I think you learned a little bit something new, but also took advantage of your prior knowledge. And so he'll be continuing that as well when he starts his job at Questech, which should also in principle be something new. But we were just talking on the phone today about how, with all his expertise in thermoelectric materials, maybe he's going to help out with a thermoelectric project again. So unfortunately, you may be seeing more of us. All right, James.
All right, awesome. Thanks so much, Jeff, for the intro. Let me just get situated really fast. All right, so thanks everyone for joining here in person, and also thank you all for joining online. Really excited to present my research to you today. I'm going to take my mask off since we're well over the 6 feet here in the front. But yeah, I want to especially thank the committee for taking so much time out of their day to listen to my dissertation today on defect engineering for more reliable and efficient lead telluride-based thermoelectric materials. So this is obviously one of those hyper-specific scientific sounding dissertation titles. So I want to take the first section here to break down a couple of the key points here for those who don't have a material science background or don't have a thermoelectrics background. So the first thing I want to touch on is what I mean by defects, and especially defect engineering. So the word defect is obviously sorry, let me fix my Zoom window here. If anybody remembers how to, oh, here we go. Okay, sorry about that. So the word defect is obviously, a common English language word that you hear in all sorts of contexts, even if you're not in a scientific field. But when I talk about defects, I'm talking about a very specific aspect of material science. So just to demonstrate the length scales I'm talking about, I have here a picture of my laptop that stopped working one day for some reason I didn't know about. So I had essentially a defective laptop. I then took my laptop, apart to try to figure out what was wrong and found that I have a defective motherboard. And then if I looked a little closer, I found out that my processor was actually a defect. So obviously these are all defects on varied length scales, but nothing like what I'm going to talk about today. We actually have to zoom in quite a bit more to get to the material science side of this. So inside of that processor, there are these chips that are grown on silicon wafers. And in the making of these wafers, you can encounter all sorts of macroscopic defects like scratches, cracks, etc., that might make this material fail. And if we actually cut this thing in half and zoomed in, 15,000 times, we could actually start to see the architecture of the silicon and the metals that make up the circuitry in that chip. I would say at this point is essentially where we cross into material science world in some regards. So at this length scale, you can start to see defects forming where the interconnects aren't properly joined and other sort of failures in the circuitry. But to get to the points in this dissertation, we have to zoom in about 1,000 more times. At this point, we'll actually start to see that silicon atoms arise, and they're kind of arranged in a very periodic structure, in a crystalline structure. However, you're going to see that the crystal is not perfect. There's all these points where atoms are missing, where foreign atoms are present in varied sites. And this is basically the length scale of defects we're going to talk about in the dissertation today. So I consider these atomic defects, point defects, and it's possible that some culmination of these defects would cause a failure and break my processor. But at the same time, they're actually completely necessary for this semiconductor to even function. So when we talk about doping semiconductors, we're talking about point defects. I'm also going to touch on dislocations, which are quite a bit harder to show in some really simple schematic like this. But here we're looking at silicon atoms, and you see near a dislocation, you essentially have a boundary across which the arrangement of the silicon atoms changes. So dislocations are kind of like a line of defects that disrupts the crystalline structure. Now, the second thing I want to get into is thermoelectric materials. So these may not be familiar to all material scientists, and I want to give a brief overview. So thermoelectric materials are used in devices to convert heat to electricity. At a very basic level, they operate as these N and P type semiconducting materials, which are put in a device that has a temperature gradient subjected to it. So some heat source and some cold side. When you have that temperature gradient, the charge carriers will actually diffuse towards the cold side of the device, which gives you a voltage gradient, which you can use to generate power. So these are have many niche applications at this point, but I think the most interesting and the one that I'm going to focus on the most here is for spaceflight. So there are space missions that are in deep space or on the surface of planets that where solar panels are not the best choice to generate power. And in those cases, thermoelectrics are actually used to harvest heat from some decaying nuclear source, which gives 24/7 reliable power for those missions. So the thermoelectric sound kind of great, but unfortunately their efficiency is quite low, and that's why we're keeping them in these sort of niche applications. As material scientists, kind of the first goal of thermoelectrics researchers is generally to increase the efficiency. And we actually have a really convenient figure of merit here that embodies the efficiency, which is called the ZT. So ZT is related to some electrical properties in the numerator, primarily, such as the electrical conductivity, which has to do with the mobility of these carriers, the Seebeck coefficient, which has to do with the voltage you get from a temperature gradient, so kind of like the energy of the carriers. And then in the denominator, we have thermal conductivity. So we want thermal conductivity to be as low as possible. And you can think of that as essentially being able to maintain a good delta T across those materials. So on a basic level, if I say ZT, higher ZT is better. That's kind of the simple fact of thermoelectrics engineering. Now, if we were to break down specifically the parts of the ZT equation that depend on electronic properties, we can see that they're actually all very dependent on the doping level. So I can make a simple model here based on the Boltzmann transport equations that demonstrates how the Seebeck conductivity and the electrical part of the thermal conductivity all depend very explicitly on the Fermi level or the doping level. So in a given system, you can make a simplified model like this that demonstrates that we need very precise control over our doping level to hit that perfect peak ZT in a given system. And also we need those doping levels to be really high. So generally, we're talking about carrier concentrations that are almost metallic, so essentially on the border of a metal and a semiconductor. If you want to actually increase the magnitude of this curve, you have to kind of look elsewhere to different material systems or try to engineer kind of the intrinsic band structure or microstructure of that material. So you could try to engineer bands such as converging bands or changing the shape of them to improve the electronic properties. And if you want to reduce the lattice thermal conductivity, which is the one thing here that to the first approximation doesn't depend on carrier concentration, you would start to add some aspects of microstructure to disrupt phonons or slow down phonons in the lattice. Now, everything I just talked about is the important parts of increasing efficiency. And I think the efficiency is kind of what the majority of people studying thermoelectrics care most about for very good reason. But there's also another aspect that I think is quite overlooked, which is the mechanical properties of thermoelectric materials. So just looking at this example segmented experimental thermoelectric device here, you see thermoelectric materials bonded to all sorts of heat sinks, welded to different parts of the device, and even bonded with other thermoelectric materials. So this thing that looks very fragile is also going to be packed into a device and launched on a rocket into space. And then it has to operate for decades without failing. So obviously there's a lot of opportunities for this thing to break, to crack, all of which would essentially ruin the properties of that device. So I believe that these mechanical properties need to be a little more of a focus going forward. I also think it's a little useful to orient people to the appearance of these materials as I talk about measuring them. So generally the thermoelectric materials I made for this thesis were through two methods, either a powder metallurgy type method where I melt together materials in a certain composition, powder them up by ball milling or hand grinding, and press them in a hot press to get these nice dense cylindrical pellets. I also have a couple instances where I grew single crystals of my material or very large grain ingots of my material in which I was able to align them and cut them up with a wire saw. And finally, the material I'm going to focus on for 95% of this talk is lead telluride. So this is kind of a legendary thermoelectric material that we've known about since the 1960s to be a good thermoelectric. And in the 1960s, we actually flew lead telluride to the moon on Apollo missions to generate power. So it has a pretty good history of success. Since the 60s, we actually have kept engineering lead telluride to maintain a very high ZT that's competitive with basically every other new system that pops up. However, you don't actually see these high ZT materials used for really any practical implementations. For example, the newest Mars rovers utilize lead telluride to generate power as well, but they actually have to use formulations more similar to that 1960s composition. This is due to a variety of reasons. So lead telluride has some issues with reliability, both making it consistently and also making sure it is mechanically robust. And also there's some reactivity and sublimation issues. So what I want to do is basically take a step back and use defect engineering to address some of those issues such that we actually can use this incredible material for practical implementation. So the first thing I want to touch on is these inconsistencies in doping N-type lead telluride. So to make lead telluride an N-type semiconductor, you can add a dopant like iodine on the tellurium site. And if everything goes according to plan, every single iodine atom would give you 1 electron, which represents perfect doping efficiency. However, you see a lot of authors who report far less than 1 electron per iodine atom in their lead telluride, which represents a really low doping efficiency. What that means in terms of performance is a sample with an identical composition but high doping efficiency can actually achieve a very high ZT, whereas the low doping efficiency sample is essentially garbage. And in fact, these high doping efficiency samples are what we believe is on the Mars rovers, whereas these low doping efficiency samples are garbage. So one key point here is these two authors on paper are making the exact same thing, but obviously the performance is drastically different. So the question I want to answer is, what is the special sauce that gives you the good material and what gives you garbage? So before I get into that, you might already guess I'm going to talk about defects being responsible. So I want to just do a brief introduction to the basic defects in lead telluride. So at 0 Kelvin, lead telluride might be this nice, perfect rock salt type structure. But like any material above 0 Kelvin, entropy necessitates that some defects form in the lattice. In lead telluride, the most common of those defects for the undoped samples are tellurium vacancies and lead vacancies. Now, because lead telluride is kind of a semiconductor, these vacancies are charged and each of them donate different types of carriers. So tellurium vacancies give you electrons, lead vacancies give you holes. So you can kind of already expect this should affect your doping properties as well. So that's what I sought to explore. I wanted to essentially recreate that bad lead telluride to prove what went wrong and make us understand how to make it better. So I did this growing single crystals of lead telluride with iodine dopants. The samples I made should have a good carrier concentration if doping goes well. And essentially I made big single crystals, I sectioned them up and I measured them. And I just want to note before I go on that this panel is basically the basic approach to making thermoelectric materials. Typically you make it, section it up and you measure it. What I wanted to do in this project is kind of take one step further and use some basic aspects of material science to do a little bit more defect engineering in these samples. So using our familiar material science tools like phase diagrams, we can look at a phase diagram of lead telluride at a normal scale and see that the 50-50 lead tellurium composition looks like an infinitesimally narrow line or a line compound. However, as I mentioned, entropy is requiring us to have defects in the lattice. So if we zoomed in several times such that our x-axis is a small fraction of a mole percent, we actually see that there is a phase width that emerges. And the phase width is governed by these different vacancies, which I mentioned earlier, such that having something that's slightly lead rich is going to be N-type, and something that's ever so slightly tellurium rich will be P-type, even without an extrinsic dopant. So I sought to control these defects in the iodine dope samples, and I used a technique that we call saturation annealing. The basic principle is that I took one of my iodine doped pellets and I sealed it in one of these quartz ampules along with some saturating media. And the saturating media contains an impurity of lead or tellurium, such that when you reach equilibrium, you essentially have a two-phase system inside this ampule. So your overall composition is kind of in this two-phase region here. And by definition, when you're in a two-phase region, the matrix composition of, say, lead telluride in this case will be fixed entirely to the lead-rich side or the tellurium-rich side, depending on how you saturation anneal. So using that technique, I demonstrated that, in fact, we can flip back and forth across a phase width with a relatively simple strategy. So I demonstrated this using some iodine-doped lead telluride that I saturation annealed to lead-rich conditions, which gives me really good N-type performance. If I take that same sample and make it tellurium rich, I actually get a P-type sample. So I've added an N-type dopant, but by making the sample tellurium rich, I've added so many lead vacancies that you don't even get the right conduction type. If I take the same exact thing and anneal it lead rich again, I actually recover most of that carrier concentration. So I can reliably flip my composition back and forth across a phase width. What that means in terms of doping efficiency is I'm getting that near perfect doping efficiency in my lead-rich samples, but abysmal doping efficiency in my tellurium-rich samples. So you can start to see where the inconsistencies arise. So whereas before I used this binary phase diagram as a useful tool to guide my defect engineering, in this case, we're actually adding a third element, so we need to look at a ternary phase diagram to try and make this same sort of a useful phase diagram tool. So I used my measured carrier concentrations along with some DFT defect calculations, which were done by Anush Goyal, which show that all of the compensation of my dopants is due to lead vacancies. So knowing that, I can reliably calculate the amount of lead vacancies I have in each of my samples and recreate a ternary phase diagram with actual compositions. So now you see in ternary phase space, the same sort of phase width becomes quite important, similar to what we have in binary phase space. And kind of the conclusion here about repeatability is basically that all of these researchers simply failed to make their samples all the way lead rich, and that's what gave them bad doping efficiency. And it's really not their fault because this phase width is so small that you can't even measure it by XRD, SEM, at least in most cases. So really what they need to do is just think about phase equilibrium and ensure their sample is ever so slightly lead rich. So kind of a simple conclusion for just lead telluride, but what it means is now we know how to reliably make this thing doped properly when it's N-type. And also understand that these basic material science defect engineering ideas should extend to really any sort of semiconductor doping. So following up that N-type work, we did a similar project in P-type lead telluride. So this oppositely doped sample is most commonly doped P-type using sodium, which should give you one hole when it replaces a lead atom in lead telluride. And this is kind of a legendary dopant. It really actually made the field advance a lot by Defect, by doing all sorts of thermoelectric span engineering, et cetera, on top of 2% doped lead telluride. So actually at the time, the solubility limit of sodium was kind of supposed to be in the vicinity of about 2 atomic percent or less. But what we have been seeing recently in both our work and in other studies is that doping beyond this 2% level actually gives you a pretty good enhancement in ZT. What that means practically is if you did all those extra band engineering and other thermoelectric engineering strategies on this newer 4% dope composition, you could potentially push the performance even higher. So we want to understand why this higher sodium concentration was actually improving performance. So of course, the first place we looked was to high temperature solubility. And we found through X-ray diffraction experiments that the lattice parameters demonstrate good solubility up to about 4 atomic percent at high temperatures. However, we don't see solubility above 2 atomic percent at room temperature. So this basically suggests sodium is diffusing more into the matrix at high temperature, and we're not able to freeze it in well when we bring back down to room temp. And I believe I'll show later Sodium we've kind of found to be a very mobile dopant, which I believe is the reason for this difficulty in freezing in high temperature equilibrium. And obviously by easy inspection, we can visually see precipitation at room temperature above about 2 atomic percent, which again suggests that we don't have that high solubility unless we're at high temps. Another effect we saw from this enhanced solubility was actually in the band structure of lead telluride. So to give a brief introduction to lead telluride's electronic bands, the conduction band of lead telluride typically consists of what we consider to be essentially one band. But if you look at the valence band, there are actually two bands that might be contributing to transport. There's both a lighter L band and a heavier sigma band. In the past, there have been several strategies to essentially expand this band gap, push the L band down in energy, and increase the convergence between these two bands, which improves thermoelectric performance. And typically this has been done with strontium, manganese, magnesium, and all of these non-doping alloying elements. What we found is actually that we have evidence this is happening from sodium doping at very high concentrations. And we see this experimentally through varied routes, but one significant one is the Hall carrier concentration, which undergoes a bipolar conduction at higher temperatures when we have more sodium, suggesting the band gap is increased. We also see that the carrier concentration is not really altered. So this means we have more sodium in the lattice, but we're not actually seeing more doping. In fact, this is most likely due to really heavy compensation by those intrinsic defects. And we also confirmed this with DFT, which was performed by Shashwat Anand, who found an enhancement in the valence band density of states from sodium doping, but not from any other of the intrinsic defects here. So essentially all the evidence together is indicating that we have this enhanced band convergence. I also performed the same sort of phase equilibrium studies in these samples where I did saturation annealing to make them lead or tellurium rich. And what we find is the ideal phase equilibrium is kind of opposite the N-type samples. So now tellurium rich saturation annealing gives you better doping and better performance, whereas lead rich saturation annealing kind of ruins your properties a bit. Okay, so keeping that all in mind, we can draw another one of these ternary phase diagram sketches. And this one is much more of a sketch because we have a lot of trouble understanding exactly how much sodium is frozen into a lattice here. But there's a couple key points that let us draw the shape of this single phase width. The first of them is that we have more than the supposed classic 2 atomic percent sodium at high temperatures in the lattice, which means our phase width should extend beyond that classic doping level. We also see that the carrier concentration is not really enhanced despite that improved solubility, which suggests we have all these intrinsic defects pulling our single phase width away from that ideal doping line. And then finally, we can do lead-rich saturation anneals to find that we essentially have a 3-phase region of poor performance in lead-rich samples. So the culmination of all this studying of intrinsic defects and electronic properties is basically that we can now understand what intrinsic defects are responsible for poor performance in some instances, and also how we might be able to engineer solubility in P-type lead telluride. Basically, this is a way to solve the inconsistencies in these samples because at a very simple level, we know N-type lead telluride should be lead-rich, P-type lead telluride should be tellurium-rich with an excess of sodium to consistently get the highest CT. These concepts they might seem specialized to lead telluride, but in reality, any person studying a compound semiconductor should worry about them. Essentially, any binary compound has a phase width due to the defects. And you can even see that in this classic gallium arsenide system, where there's a similar sort of phase width that should give you different doping properties depending on if you're gallium or arsenic rich. Okay, so moving on from the sort of thermoelectric physics side, I'm now going to talk a bit about the mechanical properties, which I mentioned earlier. So the classic thermoelectrics material science paper would generally add things like defects, microstructure, et cetera, to try to improve these thermoelectric properties to give you an optimized performance. But even in a basic, say, material science textbook, you'll find that all of these different aspects of structure are also going to affect very strongly your mechanical properties. And of course, I believe these should be a bit of a focus for actually implementing our materials for practical usages. So I'm going to now try to find a few links between these sort of structured property relationships. Now, these are very understudied in thermoelectric materials. So the mechanical properties in these systems are quite early stages at this point. But one thing we have found is that lead telluride seems to be very brittle in certain configurations. So this is something that people have found qualitatively. So if anyone has ever made lead telluride, they know if it's P-type, it's super brittle. If it's N-type, it's actually pretty robust. So beyond qualitatively, what I mean when I say brittleness is essentially that N-type lead telluride can deform much more than P-type lead telluride. And in these stress strain experiments, you can actually see that explicitly. Of course, P-type lead telluride can accommodate far less strain. These are the only 2 stress strain experiments I'm aware of in the entirety of lead telluride literature. But more often people do hardness measurements. In this case, hardness is actually a pretty good proxy of yield strength. And they often find that the hardness is far, far higher when you dope the material P-type as opposed to N-type. So essentially what this means is high hardness here corresponds to the high yield strength of P-type lead telluride. And those 2 things might sound like good properties. However, we see from these experiments that high yield strength leads to lower ductility. So in this case, we actually want to reduce hardness to make a more tough sample or do other sort of toughening mechanisms, but that hasn't really been explored yet. And to convince you that high hardness is not necessarily a good thing, I have these very scientific drop tests where I make my material and I drop it down a tube of paper. So these ingots that ultimately had a very low hardness actually don't break easily at all, even if I drop them 10 times. And the ultimate Vickers indentation I do shows instances of dislocations and plastic deformation. If I look at one of these high hardness samples, I can drop it from 3 inches and it might shatter. So these things are nowhere near as tough. And my Vickers indentations give me a higher hardness, but they also show all this brittle cracking. So what I sought to do is kind of understand what the major difference is between N-type and P-type and how we might start to probe those differences. I essentially made a ton of samples to investigate this, just kind of going in all directions. So I doped lead telluride with N-type dopants, P-type dopants, dopants that sat on different sites, the cation or anion site or interstitial sites. And in all of those samples, I also, or in the majority of them at least, I tried to control phase equilibrium. So I used methods like saturation annealing to exert some sort of control over my intrinsic defects and also my doping efficiency. I also did both single crystal and polycrystalline samples to see if grain boundaries were the main reason for this disparity. And in all my samples, I measured the Hall effect, which gives me doping levels, carrier concentrations. I measured the hardness, and I also measured the speed of sound. So speed of sound is essentially a proxy for bond strength in a material, where a material that has a higher sound velocity is generally more stiffly bonded. The first thing we found was in those speed of sound measurements. So there are a few studies that have hypothesized lead telluride is brittle when it's P-type because of the band structure. So of course, as I mentioned earlier, the valence bands of lead telluride have this unique band convergence effect, but the conduction bands do not. So I guess the idea was somehow that band convergence was altering stiffness and hardness. If this were the case, we should see the sound velocity increase with P-type carrier concentrations. And in fact, we see, if anything, a subtle decrease in sound velocity when we dope our materials P-type, and also when we dope them N-type, which may be due to charge carrier softening. But essentially what this shows is that hypothesis is just wrong, and we need to figure out what's actually going on to make these materials brittle. So where I turned was an explanation that relies on plasticity rather than elastic bonding. I think if you came fresh out of a mechanical properties class, you would probably turn to the same explanation. So we were kind of going down a wrong path for a while, I believe. Basically, the gist of this is that adding high concentrations of point defects, certain types of defects, stop dislocations from moving through a material and make it much more brittle. So I'm going to highlight a few points of all my results here. So this is a complicated plot with a lot of different dopants. We have N-type carrier concentrations on the left, P-type on the right, and no need to take it all in. I'm just going to talk about a few points of it to kind of demonstrate these 3 main clues that show us the effects of plasticity here. I should also mention right off the bat, I have both single crystal and polycrystalline samples here. Single crystals are filled with white. So obviously grain boundaries are not the main driving factor of mechanical properties here. And I should also note that the ionic radius mismatch didn't appear to be the main driving factor as well. Instead, we see these other clues such as the effect of doping with an interstitial dopant in lead telluride. So these copper and silver dopants are unique N-type dopants in that they sit on the interstitial site. And it's kind of a textbook idea that interstitials in a rock salt lattice can create this very unfavorable strain distortion for a dislocation to move through. So they're very resistant to plastic deformation. And also notably, we broke that trend of low hardness and N-type materials. So obviously we should be looking at this sort of dislocation defect interaction rather than the carrier concentrations. The other point I want to bring up is kind of a fundamental difference between N and P-type lead telluride, and that's the doping efficiency. So I showed you in the first project here that N-type lead telluride can have a very high doping efficiency, which means there are very few compensating defects. But P-type lead telluride actually never reaches the same doping efficiency. So if I wanted to get like 5 times 10 to the 19 carriers with iodine, I have to add about 0.2 atomic percent to achieve that. With sodium doping, I need an order of magnitude more doping. So essentially what that means is I have many times more doping defects in the P-type samples. And also because the low doping efficiency exists, I have many more times compensating intrinsic defects. So the gist is more low doping efficiency gives you more point defects and raises hardness by point defect dislocation interactions. And a couple of highlights to demonstrate this point further are the potassium and silver P-type dopants here. They have lower doping efficiency than these sodium dopants and correspondingly are more brittle. And also here I have an iodine dope sample that I saturation enabled to be P-type by making it tellurium rich. That gives it a ton of vacancy defects, which have made it harder than any other iodine sample I've observed in the past or anyone else has reported. Okay, and then the final key here is in essentially the distribution of certain dopants in lead telluride. So we see from some advanced atom probe tomography experiments and TEM that was performed at Aachen, Germany by Yuan Yu and Lamia, we find all this kind of aggregation of sodium dopants in our tellurium-rich sodium dope samples. So all these little dots are essentially regions where sodium is in higher concentrations. And we would expect these all to be very difficult obstacles for dislocation. If we actually look at the analog that's in lead-rich conditions, we see that the aggregation is very suppressed. So what we believe is happening here is lead-rich conditions are essentially filling some of those lead vacancy, cation vacancies, and lowering the diffusion and mobility of sodium through the material. And also just by quick visual inspection, we count more dislocations in our tellurium-rich P-type samples as opposed to the lead-rich analogs or N-type dope samples. So clearly there's all these interactions that are even just putting more dislocations in our material before we try to deform it further. And not going into any of these studies in depth, I just want to point out that this sort of atom probe tomography, identifying this aggregation or kind of clustering, it's actually been very common in thermoelectrics literature lately. People have found copper, silver, sodium, europium to all aggregate to kind of these clusters or maybe diffuse to dislocations. And in these cases, it actually improves thermoelectric properties because it's adding strain and photon scattering centers. But simultaneously, we have to think about how it might be making our materials more brittle. And we also found a little more evidence of this in a separate study, which I'm only going to talk about briefly here. But this was a neutron powder diffraction experiment I did with Riley Hannes at Oak Ridge National Lab, where we used the PowGen neutron powder diffraction beamline to get these really nice diffraction patterns for lead telluride, which we were able to refine to extract some crystallographic strain parameters. So if we just look at the room temperature here for now, on the right here, I'm showing lead telluride without a dopant that was ball milled for varied times. And we actually see this strain that kind of saturates in about 2 minutes of ball milling and doesn't go beyond that up to 15 minutes. So this strain is indicative of high dislocation densities being in that sample, which is kind of what we would expect from this plastic deformation of ball mill. We also noticed that if we added sodium or europium or a combination, that strain essentially can exceed its sort of equilibrium concentration. So clearly the presence of these point defects is causing more dislocations to be frozen in the lattice and increasing our overall strain. All right, so to conclude my mechanical property section here, I'm going to use these videos as I talk through the key points. So the first point here is that lead telluride with a high dopant efficiency dopant tends to be more robust. So for example, bismuth doping in type lead telluride gives you a very tough little ingot. If you use instead an interstitial dopant, you start to reach brittle materials. So silver, copper dopants gave me very brittle performance. On the P-type side, we have kind of a problem because they always have low doping efficiency. However, I think one potential strategy to avoid the brittleness is to make those P-type samples lead rich. So you might recall that's the bad way to make the material. In P-type samples, it actually reduces the ZT, but potentially you could still get good enough performance with better mechanical properties as opposed to the tellurium-rich sodium dope samples. So at this point, I kind of have a soft conclusion on all my work that was on lead telluride. So I'm going to summarize these are kind of the main points of my dissertation. So broadly, I would say that crystalline point defects and dislocations are somewhat underappreciated in some regards, but are really hold the key to making these materials consistently and making them brittle or ductile. So we actually have these sort of defect engineering strategies now, like changing phase equilibrium or doping on specific sites that can help us tune those properties to improve the material or understand why it's bad. So in the beginning here, I had a laptop that didn't work and there was nothing I could do about it. I don't know what defects are responsible for that. But I find that after this dissertation on lead telluride, I essentially got redemption. So now if I have a really bad lead telluride sample, I can understand how to improve it, essentially fix that material. And at the end of the day, the strategies I'm using are these somewhat simple strategies, but they're tuning atomic concentrations, which is kind of an interesting thing to do from such a high up level to engineer defects in these materials. Now I have one more project I want to highlight. So now we're not talking about lead telluride, so it kind of deserves a separate section. But I recently completed some work with NASA JPL during a virtual internship, which would have been nice and warm if I could go in person, but then of course we had COVID. So in this project, we investigated rare earth telluride thermoelectric materials. So these are really promising next generation thermoelectric materials that typically have lanthanum, praseodymium, or neodymium as a rare earth element. And lanthanum telluride is kind of the best studied of the three. And you can see that its ZT is incredibly high at very high temperatures. So this could potentially give you great performance for really deep space, high temperature space applications. Now, the thing I find most interesting about this material class is the ability to accommodate vacancies in the cation site. You might recall I showed you a lead telluride phase diagram earlier that was super, super narrow, and you had to zoom in to see the phase width. In these 3-4 structure type rare earth telluride materials, you actually see the phase width without even zooming in. So it can accommodate tons of vacancies without actually changing its phase. In terms of electronic properties, that means the most lanthanum-rich materials, which are the 3-4 composition, have very high carrier concentrations, almost like a metal. Whereas going all the way to the tellurium-rich side gives you this 2-3 composition that's still in the same phase actually. That's kind of like an undoped semiconductor. And the main question here was, like lead telluride, people had this qualitative idea of mechanical properties in the system, where in this case, rare earth tellurides with more vacancies were more brittle. So I wanted to try to use the same sort of approaches to explain that qualitative field again in this system. So the first thing I did was turn to the sound velocity measurements. So I received some lanthanum, praseodymium, and neodymium doped samples from Bria Hogan at JPL and UCLA. And I measured the sound velocity through all of them. And what I find is actually sound velocity increases as I add vacancies. This is kind of not what you might expect at first glance, because more vacancies should weaken your structure. But there's actually a good explanation for this in the charge carrier levels. So remember, as we add vacancies, we're also removing electrons from our structure. So that means higher X vacancies are really similar to being a low doped semiconductor material. We actually recently published this paper showing that high carrier concentrations in thermoelectric materials can lead to softening of sound velocity, which is likely due to essentially those extra carriers affecting bonding, occupying antibonding orbitals, et cetera. And I thought this is a very fitting paper for today because every member of the committee is listed as a PI. So this is a great room of collaboration here. But anyway, so that's what we believe is happening here. The effect of charge carrier softening is stronger than the effect of removing those cations. There's actually an interesting practical consequence of this in the thermal expansion coefficient. So as you stiffen a material, you would expect the material to expand less with temperature. And from high temperature X-ray diffraction, I found that that is indeed the case. We can actually reduce thermal expansion by adding vacancies. This is actually potentially useful for improving the usefulness of these materials in modules where you need to match thermal expansion coefficients between different parts of the material. Now, turning to mechanical properties, we get some pretty interesting results. So I used, again, these Vickers hardness tests, similar to what I did in lead telluride. And I found that the hardness decreases with increasing vacancy concentration. And also the fracture toughness decreases quite a bit. So to briefly touch on fracture toughness, this is essentially a measure of how easily a crack can open through a material. And I was actually able to measure this in lanthanum telluride because it has this nice ceramic type cracking behavior at the indentation tips of my Vickers indents. You can actually measure these crack lengths to get an estimation of fracture toughness. But basically, reduced fracture toughness means the thing cracks and breaks far more easily. So clearly, our results are pretty much confirming what we believed qualitatively, but have never actually measured, which is that they get more brittle with vacancies. Now, these sort of results that are going opposite the direction of sound velocity aren't necessarily what you would expect in a single like metal or ceramic in typical mechanical properties literature. But a major difference here is we're essentially changing a material from a metal to a semiconductor as we add vacancies. There's really no other system that I've ever found explored where you can explore how mechanical properties change as such an aggressive change of doping occurs. So I believe these sorts of widely dopable thermoelectric materials are quite interesting for studying mechanical properties. And hopefully this study brings up some interesting points. Okay, so that concludes basically the majority of my dissertation work that I wanted to share today. But before we wrap up, I just have to take some time to thank everyone who helped me get to this point. So first off, all the people here played really instrumental parts in collaborating on these projects. You know, some of the results I show are their results. So they were really instrumental in publishing these papers. Also want to acknowledge the general funding agencies, CHIMAD, NASA, and the DEMREF and GHOST meeting folks who were really great to meet along the way and great to chat with weekly through meetings. I also have to thank Jeff and the group. It's been a real pleasure to work in this group, and I'm really happy that Jeff is able to make such a great welcoming environment. I can really tell he's a proper science nerd. He loves science, but he also, I think he's passionate about science, but also you can tell he's passionate about students getting the best PhD that they can out of their work. He really wants us to succeed on our own terms, and I appreciate that. Also, I have many of the older group members listed here. I want to thank everyone in the group for making such a great environment. And then a few of these older fellows were really great mentors to me. They taught me what to do in the lab, how to act at conferences, understand how to talk to people and everything. And also I have to thank my friends who, of course, have been really important throughout this whole PhD, starting from the first day of school pick and growing to hiking Half Dome. And also, my friends back from college and at home who I'm happy to still see whenever I go back, and my partner Danielle, and for doing tech support today also. And then finally, my family. I'm really happy they could come today. But just a really great, humble, and generous group of people. Very COVID safe as well. And yeah, and you know, they had kind of a love for nature and also being nerds, which helped me kind of find my own path here.
Is that the garage SEM?
Yeah. So that's Barry Mail, the garage SEM operator. So I got a lot of exposure early on, thanks to him. And my plan for after Northwestern is, I'm not taking a big leap, I'm taking tiny steps, and I'm going about a mile away from campus to Quest Tech Innovations, where I'm going to be doing kind of more computational design of materials. I'll have a thermoelectrics project, as Jeff mentioned, but also expanding a little more into you know, metals and alloys and whatnot. And with that, I'd like to thank everyone here online and in person, and happy to take anyone's questions.
Perfect timing.
Nice.
All that practice pays off. Yes, questions?
Yeah, thanks, James. That was really cool. I have a question on the conclusion of your first section. So I think it was slide 18. Basically, obviously, you're talking about being able to control and flip-flop between the N type and the P type of saturation and annealing and like lead rich, clear rich. And I was wondering how, like, once you like get your material to that composition, how stable it is there. Obviously, we're talking about operation for hundreds or thousands of hours at potentially very extreme conditions, and obviously, like, defects are mobile. That's the whole point. So I'm wondering if there's been studies on the stability of that composition, or if there's kind of like drift, you know, if they drift exactly that one, if they drift back and be towards the middle from the extremes, or if they're relatively stable conditions.
Yeah, so there is, you can consider essentially the vapor pressure of, say, lead or tellurium or whatever other ternaries exist in the ternary phase diagram. And we don't know exactly how much composition drifts, but I would say this is going to be somewhat qualitative, but lead-rich N-type lead telluride is actually very robust. Several cycles doesn't change the thermoelectric properties, whereas lead telluride that's all the way tellurium-rich actually starts to drift towards the lead-rich phase boundary. And I think that's why I got P-type conduction here, but these guys got bad N-type. So I believe the amount of drift is equivalent to essentially the space between my points and theirs. So yeah, that has to do with the tellurium vapor pressure. I also think some of the people who are accidentally making good material, seems like they did all these vacuum annealing procedures. So they might have been, you know, subliming off a little bit of that extra tellurium, which happened to make them hit the right composition.
Sure.
So a bit of a follow-up on Jenny's question. You measure directly this very precise level of doping.
Yeah, so we use Hall carrier concentration measurements, which aren't perfect. So, you know, there's a kind of a corollary here that this is a sketch. Hall carrier concentration gives you a sense of the number of dopants you have, but it also depends somewhat on the band structure. So potentially these things should all be reduced by like 1.2 or so. And you can model how much the band structure affects your carrier concentrations. However, if you're starting with Hall carrier concentrations and everyone's using them, it's a pretty good indication of phase widths. So no, it's not perfect, but it's, in my mind, it's the easiest and best way to get at this.
It's standard.
Yeah, essentially. That's where this phase diagram actually comes from, Hall carrier concentration measurements. So you can't measure this in an SEM. It's like impossible. So you have to turn to the charge carriers.
Yes. Is there a significant drop off or just kind of over time noticing that electrics degrade in use? Because you said that these are used for decades.
Yeah. It depends a lot on the material. So if they're in the vacuum of space and they're prone to sublimation, then yeah, absolutely. For example, like I mentioned, P-type lead telluride, the high ZT stuff, isn't really used in NASA missions now. Part of the reason is because it sublimes quite easily. And I didn't get into that part here. So that's a whole important aspect of the P-type lead telluride. But the N-type samples seem fine. So it's likely due to the vapor pressures in the phase equilibrium you're in that kind of suppresses loss of material. And I'm sure they lose a bit, and the people on here from JPL probably know way better than I do how much it loses, but in my experience, it's not quite as bad.
When you were talking about the link comment and other rights for NASA JPL, we're talking about buying applications for them. What factors do they when they're
Yeah, there's actually this question of cost when you're designing one of these things. So the radioactive decaying materials like plutonium-238 or something, it's super expensive. So if you can afford to use more of it, you can get a way higher temperature and then you get better performance. But you can see from these curves, ideally, lanthanum telluride should be about 1000 C or so. So that's kind of the goal. These aren't actually used in devices for NASA yet. They're future, so I'm not exactly sure what the temperature will be. Oh, I'm sorry, Saba. I forgot to repeat the questions. Saba, so let's see. We had questions about long-term stability, and that's why I was talking about vapor pressure. And then we just got a question about how hot the device will be for rare earth telluride thermoelectric materials. And I also see a hand raised from Matthias in here. So Matthias, you can say it out loud.
Hi, James.
Hey.
Awesome talk. That was really great. It was really great to also catch up on a lot of the stuff that you've done in the last half of your PhD, which I was not so involved with. But I'm really loving the direction that you went with all of this mechanical property stuff and parsing out how both N and P type electronic behavior ties into the mechanical properties that would lead to a material being robust enough for various applications. And I know that we talk about compatibility factor in thermoelectrics a lot of times, which is usually looking at things like thermal expansion. I don't know if fracture toughness and these kinds of properties are currently considered in a quality factor. But I was just wondering, with all of your expertise in like P and N type materials, being able to put two materials together that would work well in a thermoelectric module, what direction would you go in like expanding the constant quality factor?
Yeah, that's a great question. So yeah, usually when we think about materials working together, like Matthias said, we essentially only look at thermal expansion and then some compatibility factor, which has to do more with some other aspects of thermoelectric physics. So I would love to put fracture toughness in there and hardness, but the error bars on fracture toughness are so big and there's so little data on it that I don't really think it's that useful a measurement for broad comparisons, unless you do like a vague kind of like an estimation, which you and Leah are familiar with doing these estimations. I think maybe Vickers hardness is pretty universal and easy to do. Although it's not really a big deal if the Vickers hardness is super different between the two samples. So I honestly think thermal expansion is still what I would be most interested in. It's almost like what we have in there that Jeff would have worked out in the past was actually a pretty good idea. but if your sample is really low fracture toughness, you shouldn't even use it in the first place.
Yeah, thanks. There's definitely a lot of interesting stuff in there with tying mechanical properties to the overall thermoelectric performance. So thanks for that.
Yeah, thank you.
Yes.
So,
That's you.
I'm curious what the Curiosity and Perseverance robots, how they have performed with regards to their thermoelectrics. I wonder if you comment if they've had issues perhaps with some of these mechanical properties?
Yeah, so
Would you repeat the question?
right, so the question was, how are Curiosity and Perseverance doing right now in terms of mechanical properties? So I don't know exact specifics, but they do use these somewhat lower ZT formulations because those are a little more robust than the high ZT stuff. So they kind of address the issue at the start. Although I believe the P-type materials are degrading somewhat. So it's not perfect, but Curiosity has been up there for what, 10 years? And it still works. So it's, yeah, where they don't like the other rovers, you know, like Opportunity has to wait for Martian dust storms to clean off its solar panels, you know, but thermoelectric material, you don't have to do that. It's like a little nuclear power plant in the back of your device, of your robot. But yeah, I'm not exactly sure of specifics, but it works okay. And I've seen like a future plan for some Europa mission to use the same thermoelectric module they have on those robots, so it must be fairly successful.
Yeah. it sounds
Yeah.
like. Thank you.
Yeah, so it's interesting to me because those lead tellurides that you're talking about used in the 60s were, you know, that was, you know, 60 years ago now, right? So the people that made those and the companies that made those are totally different today than they were back then. And I'm kind of curious as to, you know, whether they, you know, I don't think they understood half of this, right? So in their recipes, they may have talked about adding extra lead as part of what they're doing, but I don't think they understood it to the degree now. And so now with, you know, with your knowledge of what the defects are doing to the hardness and the brittleness, the fracture toughness, that, you know, you would think that that would affect how they make the materials. So in your design flow chart, you know, how you optimize those materials should be different today than what was back then. So
Yeah.
kind of curious as to, you know, if even that material performs as well as it used to in the 60s or maybe better because of different optimizations.
Yeah. Yeah, there's the 60 stuff was made by 3M, which obviously doesn't make thermoelectrics anymore, but there is an old paper in Mud Library where they say it's an extra lead, but they didn't have the right reason. They just said it was better. So I think Saba, did you have something to add?
Well, yeah, I put some things in the chat. So in terms of Curiosity and Perseverance, they're doing great on the Mars surface. So a few things that they have to, that's helping them out is that the couples are actually spring loaded. So they're under compression the entire time. So that really helps with any kind of mechanical like issues that, and the weakness and the brittleness of lead telluride in tags. And for the most part, the two biggest events where the couples and the generator was experiencing the most vibration and stress was during the pyroshock events. So there's an aeroshell that's covering the rover. And so you have a series of pyrotechnics that are initiated to release the aeroshell. So that's a huge amount of vibrations there. And then also during the entry, landing, and descent sequence, we have a series of pyroshock events again. So those are the two stressful states, and we've tested them and engineered them, and their lead telluride system is fine. So he keeps going, and they're doing really well.
Awesome, thanks. Yeah, I wasn't aware of that. So interesting.
All right, well, thank you, James. We will shut down the open session and move to a closed session. Thank you very much.